Hello there, and welcome to the Sleepy Space Channel. Tonight, the whole history of the universe, from its very first instant to its last dim light, laid end to end in a single unbroken evening. 13.8 billion years of it, told slowly and in order. We will begin before there were stars, in the first hot fraction of a second, and move through the first 3 minutes, the long fog and the moment it cleared, the first stars, the gathering of the galaxies, the making of everything that worlds are built from, and the quiet arrival of our own sun. And then, gently, we will follow the story past the present, into the unresolved reaches of the far future. If you find these slow journeys through time worth your evening, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is something you need to hold on to. There is nowhere the night has to reach, and nothing here to carry. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away behind you. Let's begin. The universe begins hot and dense and small beyond the ordinary meaning of the word. Everything that will ever exist is gathered into this beginning. Every galaxy that will one day turn in the dark is here. Every atom that will one day settle into a stone, or a sea, or the body of a listener, is present in this first moment, though none of it yet wears the form we would recognize. There are no stars. There are no worlds. There is not yet even the empty space between things, in the way we usually picture it. There is only a single, seamless, unimaginably hot state, and the quiet fact that it is already changing. It helps, at the start, to set aside one familiar picture. The beginning of the universe was not an explosion that happened at a particular place, throwing matter outward into a waiting room of empty space. There was no waiting room. There was no outside. Space itself is the thing that grows. When we say the universe expands, we do not mean that its contents fly apart through space. We mean that space itself stretches, carrying everything with it, the way a slowly rising loaf carries every raisin gently away from every other. The story of the universe is not the story of an explosion in a room. It is the story of the room itself, swelling. At this earliest moment, the conditions are so extreme that our best understanding of physics reaches its edge. The temperature is higher than any furnace, higher than the core of any star that will ever form. The density is beyond anything that survives into later times. Under such conditions, the forces that shape the universe as we know it are thought to lose their separate identities. Gravity, and the force that binds light to matter, and the two forces that will one day govern the cores of atoms, are believed to be woven together into a single behavior, indistinguishable from one another. This first sliver of time is the one true frontier of the whole story, the one chapter we cannot yet read in full. What we can say is that the universe cools. This single fact is the engine of everything that follows. As space stretches, the heat within it spreads thinner, and the temperature falls. Nearly every important event in the long history to come is something that becomes possible only when the universe has cooled past a certain point. The forming of particles, the making of atoms, the lighting of the first stars, the slow gathering of galaxies, all of it waits on the temperature dropping low enough. From the very first moment, the universe is on a long, patient slope from hot toward cold, and time itself can almost be read as the falling of that temperature. In the earliest instant we can describe, there is a period thought to have shaped everything that came after, though it lasted for the smallest fraction of a second. The universe went through a phase of staggering growth, doubling in size, and doubling again and again, faster than the mind can hold, in far less than the blink of an eye. This early swelling is called inflation. In that fleeting interval, a patch, smaller than anything imaginable, was stretched to enormous size, and the shape of the cosmos was set. Inflation quietly answers several puzzles at once, which is part of why it is trusted. It explains why the universe looks so evenly balanced in every direction. When we measure the sky on one side and compare it to the far opposite side, the two regions look remarkably alike, as though they had once been close enough to settle into agreement. And indeed they had. Before inflation stretched them apart, those regions were neighbors, sharing warmth, evening out their differences. The great sameness of the sky is the memory of that early closeness pulled across the whole cosmos by inflation's sudden stretch. Inflation also explains why space is so nearly flat and level, without the curvature one might expect, and why the universe is not littered with strange leftover relics from its first moments. Whatever wrinkles or oddities might have existed in the beginning, inflation smoothed them out, stretching them so thin that they effectively vanished. A crumpled sheet, pulled hard enough at its corners, comes out smooth. The universe we live in carries that smoothness as a kind of inheritance. But the most important thing inflation did was almost the opposite of smoothing. At the smallest scale, the universe is never perfectly still. There is a faint, restless trembling built into the fabric of things, tiny fluctuations that flicker in and out at the finest level. Inflation took these minute trembles and stretched them too, magnifying them from something smaller than a particle into gentle ripples spread across the entire sky. These faint unevennesses, some regions ending up a whisper denser than others, are the single most important legacy of the first instant. They are the seeds. Every galaxy that will ever form, every cluster of galaxies, every long thread of the cosmic web, grows from these gentle variations laid down before the universe was a single second old. There is something quietly moving in that. The grandest structures that will ever exist begin as the smallest imaginable trembles. The great wheels of galaxies, turning slowly for billions of years, trace their origin to random flickers at the edge of the very small, frozen into the young universe by its first burst of growth. Nothing was designed. The pattern of everything to come was sketched by chance and then enlarged. As inflation ends, the enormous energy that drove it does not simply disappear. It pours into the young universe as heat and matter, filling it with a dense, glowing bath of particles. The cosmos is reheated into a seething plasma, a crowded sea of the smallest building blocks of matter, all of them interacting constantly, colliding and rebounding, too hot and too crowded to hold any lasting form. This is the universe at its most elemental, a smooth, hot fluid of energy with the whole future folded invisibly inside it. Within this hot sea, a subtle imbalance appears, and it matters more than almost anything else in the story. For every kind of particle of matter, there is a mirror counterpart, a particle of antimatter, its exact opposite. When a particle meets its antiparticle, the two annihilate, vanishing in a flash of light. In the young universe, matter and antimatter are made in nearly equal numbers, and so nearly all of it cancels away, particle meeting antiparticle, both dissolving into radiation. But the balance is not quite perfect. For reasons still not fully understood, matter slightly outnumbers antimatter by only about 1 part in a billion. That tiny surplus is everything. When the great annihilation runs its course and the light of all that cancellation streams outward, what remains is only the leftover billionth, the small excess of matter that had no antimatter partner to meet. Everything solid that will ever exist, every star, every planet, every grain of dust and drop of water is built from that faint remainder. We are, quite literally, what was left over after the universe nearly erased itself. The whole visible cosmos is a survivor, the small fraction that escaped the mirror. It is worth staying a moment longer with what cooling actually does, because it is the hidden logic of the whole story. When the universe was at its hottest, the forces that shape it were merged, indistinguishable from one another. As it cooled, those forces separated, one after another, each becoming its own distinct behavior as the temperature crossed the threshold that let it stand apart. Gravity is thought to have taken on its separate character first, then the force that binds atomic nuclei, then the others, until the familiar four we know today had each emerged. The universe did not gain its structure all at once. It gained it gradually, as a warm thing gains its shape while it settles. There is a useful way to think about the expansion that helps the mind hold it. Because space itself stretches, any light traveling through it is stretched as well, its waves drawn out longer and its color shifted toward the red. This means the light from more distant things, which has traveled through more stretching space, arrives more reddened than the light from nearer things. This gentle reddening is one of the surest signs that the universe expands, and it works like a kind of clock. The more a light has been stretched, the longer it has traveled, and the further back toward the beginning we are looking when we receive it. That relationship lets us do something quietly remarkable. We can, in a sense, run the film of the universe backward. If everything is drifting apart and cooling now, then in the past, everything was closer together and hotter. Follow that logic back far enough, and all of the universe converges toward a single, hot, dense beginning. We do not reach that beginning by guessing. We reach it by taking what we see today, the expansion, the cooling, the reddened light, and carefully reversing it, step by step, until the whole cosmos gathers back into the fierce, small, hot state where the story begins. There is a further comfort in how orderly this cooling was once one sees the pattern of it. Nothing about the early universe was chaotic in the way the word beginning might suggest. It was, if anything, remarkably smooth and even, a warm, uniform state passing through one gentle threshold after another as it cooled. Each threshold allowed something new to become possible, and the universe took each step in turn, without haste and without disorder. The making of the forces, the settling of the particles, the writing of the light element recipe, all of it followed as the temperature fell in a sequence as steady as the cooling of any warm thing left in a cool place. The universe did not begin in violence. It began in heat, and then it quietly cooled, and everything followed from that. The very smallness of the beginning is difficult to picture, and it helps to be gentle about it. Everything we can now see, the entire observable universe with its uncountable galaxies, traces back to a region that was, at the start, extraordinarily compact. It was not sitting in a larger, empty space. It was everything there was, and it has been growing ever since, carrying its contents apart as it grows. The distance between any two specks of matter today is the accumulated result of all that patient stretching added up across nearly 14 billion years. And through all of it, the faint seeds laid down by inflation are riding along, waiting. They are too gentle to notice in this early heat, mere whispers of unevenness in an almost perfectly smooth sea. But they are the most patient things in the universe. They will survive the first 3 minutes, and the long fog, and the clearing of that fog unchanged in their essential pattern, until at last, ages later, gravity begins to work upon them in the dark. Everything grand that is coming is already sketched, faintly, in these first trembles. The universe has written its opening line, and it will spend the rest of time reading it aloud. By now, though still within the first moments, the universe has laid its foundation. It has set its size and its smoothness. It has planted the seeds of all future structure. It has kept its small surplus of matter and let the rest annihilate into a flood of light. It has begun its long descent from hot toward cold. Nothing yet shines in the way a star shines. Nothing yet holds together in the way a world holds together. But the raw conditions are in place, and the temperature is still falling, steadily, quietly, opening the way to the next chapter. And in that next chapter, in only a few minutes of cosmic time, the universe will begin, for the first time, to assemble the pieces of ordinary matter into something that lasts. We come now to the fastest, most productive stretch of the entire story. In less time than it takes to soft-boil an egg, the universe assembles the basic material of every atom that will ever be. In the first 3 minutes, the recipe of ordinary matter is written, and once written, it will hold, almost unchanged, for billions of years. Everything that stars will later do, all their patient forging of heavier elements, is only a slow addition to what these first 3 minutes set down. At the opening of this chapter, the universe is still a smooth, glowing plasma, but it is a plasma of the very smallest pieces. The particles we now call the building blocks of matter, the quarks, are not yet bound into anything. They drift free in the heat, too energetic to hold together, colliding and parting again. Alongside them are the lighter particles, the electrons and their kin, and everywhere the constant flood of light. It is a featureless, even sea, but it is cooling, and cooling is about to allow the first lasting things to form. As the temperature falls, the quarks can no longer resist binding. They lock together in groups of 3, and in doing so, they form the first stable familiar particles, the protons and the neutrons. These are the pieces from which every atomic nucleus will ever be made. It is a quiet moment, without drama, but it is one of the great thresholds of the story. Before it, matter had no permanent form. After it, the universe holds particles that will endure, in some cases, for the entire length of time that follows. The proton deserves a moment of attention, because a proton is something very familiar in disguise. A single proton, all by itself, is simply the nucleus of a hydrogen atom, the lightest and most common substance in the universe. This means that hydrogen, in its simplest form, is essentially finished here, in the first moments. The most abundant material in all of existence, the gas from which stars and galaxies will later be built, is settled almost at the very beginning and has remained the majority of ordinary matter ever since. When you picture the universe filling with hydrogen, you are picturing something decided in these first instants. The neutron is a near twin of the proton, but with a small and important difference. It is very slightly heavier, and when a neutron is left on its own, outside the shelter of a nucleus, it does not last. After a matter of minutes, a lone neutron breaks down, transforming into a proton and lighter particles. This sets a kind of clock ticking. Any neutron that fails to find a safe home inside a nucleus in the next few minutes will simply vanish. The universe has only a brief window in which to build anything that needs neutrons, and that window is closing even as it opens. And so the second great event of these minutes begins, the building of the first nuclei. As protons and neutrons move through the cooling plasma, they begin to stick, fusing together into small combinations. A proton and a neutron join to make a heavier form of hydrogen. These in turn combine, step by step, climbing toward helium, the next element up the ladder. For these few minutes, and only these few minutes, the entire universe behaves like the core of a star, fusing light particles into heavier ones everywhere at once. Never again will fusion happen across all of space in this way. From here on, fusion will be the private work of stars. But the building does not climb very far. The window is short and the neutrons are limited, and the expanding universe is cooling and thinning even as the fusion proceeds. Before the process can reach the heavier elements, the temperature and density drop too low for fusion to continue, and the reactions stop. What is left is a fixed and simple recipe. About 3/4 of ordinary matter ends up as hydrogen. About 1/4 ends up as helium. And only the faintest trace goes into the next elements, a little lithium and a whisper of one or two others. That is essentially all. The universe emerges from its first minutes made almost entirely of the two lightest elements, and it will stay that way until stars arrive to change the balance. There is a real elegance in how simple this starting recipe is, and in how well it holds up. When we look out across the sky today and measure the makeup of the oldest, least altered gas we can find, we see almost exactly these proportions, roughly 3 parts hydrogen to 1 part helium, with only traces of anything heavier. That match between what a hot young universe should have cooked in its first minutes and what we still measure in the quiet gas between galaxies is one of the strongest reasons to trust the whole picture of a hot beginning. The universe kept a record of its own first minutes, written in the ratio of its lightest elements, and we can still read it. It is worth pausing on what this means. Everything the universe is made of, at its most basic level, is decided in the first 3 minutes. The rest of the story, the whole long procession of stars and galaxies and worlds across nearly 14 billion years, is not about making new raw material from nothing. It is about what that first simple material slowly does, once gravity and time are given room to work on it. The hydrogen that will one day burn in the first stars, the hydrogen that will one day become part of an ocean, is already here, formed and waiting, before the universe is even 5 minutes old. Yet for all that has been accomplished, the universe of these early minutes is still not a place we would recognize. It is far too hot for atoms to exist. An atom needs its electrons to settle quietly around its nucleus. And here, the electrons are still far too energetic to be captured. They fly free through the plasma, unattached, restless. And free electrons have a particular effect on light. They scatter it. A ray of light in this early universe cannot travel any real distance before it strikes a free electron and is knocked in a new direction, and then another, and then another. Because of this, the universe of these early minutes is not clear. It is opaque. It glows from within, evenly and brightly, but you cannot see through it. If you could somehow stand inside it and open your eyes, you would find yourself surrounded by a featureless, glowing fog, bright in every direction, with nothing visible beyond the space right around you. Light is everywhere, but it goes nowhere in particular, forever bouncing among the free electrons. The universe is luminous and blind at the same time. This fog is not a passing thing. Having moved through its first minutes at tremendous speed, the universe now enters a long, slow stretch in which almost nothing seems to change on the surface. The blazing fog persists not for minutes, but for hundreds of thousands of years, cooling all the while, dimming very gradually as it goes. The frantic pace of the first minutes gives way to patience. The universe has made its matter, set its recipe, and now it simply waits, glowing softly, expanding and cooling, moving with immense slowness toward the moment when the fog will finally lift. There is a detail in this early cooking that rewards a closer look, because it shows how delicately the recipe was balanced. Before the nuclei could build, the universe had to settle the proportion of neutrons to protons, and that proportion was set by temperature. While the universe was hot enough, neutrons and protons converted back and forth into one another freely, staying in balance. As it cooled, that free conversion slowed and then effectively stopped, freezing the ratio at a particular value. It is from that frozen ratio and the swift decay of any lonely neutrons that the final amounts of hydrogen and helium follow. The universe set the dial early, and everything downstream obeyed it. The first step up the ladder is also the most fragile, and it acts as a kind of gate. Before helium can form, protons and neutrons must first join into a heavier form of hydrogen, and this heavier hydrogen is easily broken apart by the intense radiation that fills the young universe. For a while, it is made and destroyed almost as fast as it forms, and the ladder cannot be climbed. Only once the universe cools enough that this fragile first rung survives can the building rush forward to helium. So the whole process waits on a bottleneck, and then, when the gate opens, moves quickly through it. Because helium is so stable and so easy to reach once the gate is open, nearly all of the available neutrons end up locked inside it. This is why helium comes out at close to a quarter of ordinary matter, and why almost nothing climbs past it. The heavier rungs would need conditions that the expanding, cooling universe no longer provides. The window has already begun to close by the time helium is finished, and the reactions simply run out of the heat and density they need. The recipe stops where it stops, not by design, but because the universe cooled through the opportunity. The traces left behind are small but precious to us, because they are so sensitive to the conditions of these minutes. The tiny surviving amount of the fragile, heavier hydrogen, in particular, is a delicate record. Had the young universe been a little denser, more of it would have been consumed and less would survive. Its faint presence in the oldest gas, measured carefully, tells us how dense the universe was in its first minutes, a number written into the cosmos before there were any stars to witness it. The universe kept a receipt of its own early bookkeeping. All of this happens remarkably, while the universe is still perfectly smooth, still without a single star or structure. There is nothing here but the even glowing plasma and the physics of heat and cooling, running everywhere at once, in exactly the same way in every direction. The making of the light elements is the one great chemical event that the whole universe performs in unison, before it has any parts. After this, the universe will never again do anything as one. From the first stars onward, its history becomes a history of separate places, each with its own story. But the light elements belong to all of it equally, made in a single shared act at the very start. And when it is done, the universe carries this settled composition forward through everything that comes next, unchanged for an enormous span of time. The gas that drifts through the long fog is this gas. The gas that gathers in the dark age is this gas. The gas that finally lights the first stars is this gas, 3 parts hydrogen to 1 part helium, still carrying the proportions set in the first 3 minutes. Only when stars begin to forge new elements will the balance finally, slowly, start to shift. Until then, the universe wears the composition of its own infancy, held steady across the long, dark, patient years to come. And so the first 3 minutes close, not with a flourish, but with a quiet settling. The pieces of every future atom are in place. The proportions of the elements are fixed. The universe is a smooth, warm, glowing sea of hydrogen and helium plasma, threaded everywhere with light that cannot yet escape. The seeds planted in the first instant are still there, the faint, denser patches waiting silently within the glow. Nothing shines on its own yet. Nothing has gathered into a shape. But the slow cooling continues, unhurried and sure, carrying the universe toward the moment when, for the very first time, it will become clear, and its oldest light will be set free to travel. For a long age after its first minutes, the universe is a smooth, glowing plasma, cooling with immense slowness. Nothing about it seems to move. There are no stars to light it, no structures to break its evenness, only the warm, even glow of trapped light and the free electrons that keep that light from ever escaping. And then, after hundreds of thousands of years of this patient dimming, a single threshold is crossed, and everything changes at once. The fog lifts. The oldest light in existence is set free. And that light, released in a moment long ago, is still arriving here tonight. The change comes down to temperature, as so many changes do. All through the long fog, the universe has been cooling, and the free electrons have been slowing. There comes a point when the plasma is finally cool enough that the electrons can no longer resist being captured. Nuclei reach out, so to speak, and hold them. Protons capture electrons and become complete hydrogen atoms. Helium nuclei capture their electrons as well. Across the whole universe, at nearly the same time, the free electrons are gathered up and bound quietly into atoms. This settling of electrons into atoms is one of the great quiet turning points of the story. The effect on light is immediate and total. The reason the universe was opaque was the swarm of free electrons endlessly scattering every ray. But once the electrons are tucked into atoms, that swarm is gone. There is suddenly nothing to deflect the light. A ray that a moment before could not travel any distance at all can now cross the universe unhindered. In an interval that is brief, by the measure of what came before, the glowing fog becomes a clear night. Space, for the first time, is transparent, and all the light that had been trapped within the fog, bouncing among the electrons for hundreds of thousands of years, is released in that moment to travel freely. It streams outward in every direction across a newly clear cosmos, and having nothing left to stop it, it simply keeps going. It does not fade away or come to rest. It travels on, across all the ages that follow, still moving through the universe today. This released light is the oldest thing that anyone can see. We give it a plain name, the cosmic microwave background, but the plainness of the name hides what it is. It is a direct picture of the universe at the instant it turned clear, a photograph taken before there were any stars, developed slowly over billions of years, and delivered to us at last. It fills the entire sky. There is no direction you can look in which it is not present, arriving faintly and steadily from the edge of time. Over the long ages of its travel, this oldest light has changed in one way. The universe has kept expanding, and as space stretched, it stretched the light along with it, drawing out its waves, cooling it, lowering it from the brilliant glow it once was into something far gentler. What began as a fierce light has been softened by billions of years of expansion into a faint hum of microwaves, cold and quiet, just barely above the lowest temperature there is. The fire of the young universe reaches us now as the faintest possible warmth, spread evenly across the whole sky. There is something quietly astonishing in this, worth holding for a moment. That ancient light is falling on everything, everywhere, right now. It is landing on every rooftop and every hillside and every dark stretch of ocean at this very moment, arriving from all directions at once, having traveled since before the first star was born. It passes through the night, unnoticed, a whisper of the universe's beginning, brushing against the present, constant and gentle, and old beyond reckoning. And there is more written into that light than its warmth. Woven through it are the seeds, the faint unevennesses laid down in the first instant and carried patiently through the fog. In the oldest light, some patches are a whisper warmer and some a whisper cooler than the average. And these tiny differences are the imprint of those first gentle ripples, frozen into place at the moment the universe turned clear. When we map that faint pattern across the sky, we are looking at the blueprint of everything to come. The gentle unevenness from which all galaxies will eventually grow, preserved in the light of the young universe. But once the light departs, the universe enters its darkest age. This is a point often missed, and it is worth dwelling on gently. When the fog cleared, the universe did not fill with the starry sky we know. It filled with nothing that shines at all. The light that was released simply left, streaming outward, and behind it lay only cool, clear gas, hydrogen and helium drifting quietly in the dark, with no source of new light anywhere. There were no stars. There were no galaxies. There was nothing burning, nothing glowing, nothing to break the darkness. This is the cosmic dark age, and it is the darkest the universe will ever be. Before this, everything glowed, held in the fire of the fog. After this, stars will fill the cosmos with light. But in between lies a long, still interval of true darkness, lit by nothing, warmed only by the fading afterglow that is already slipping away toward the cold. If you could have stood within the universe then, you would have seen nothing at all, only clear black space in every direction, and cold gas you could not see, drifting through it. Yet the dark age is not empty of activity, and this is the quiet secret of the chapter. Though nothing shines, something is at work, patiently and invisibly. Gravity does not need light. In the slightly denser patches, the seeds carried all the way from the first instant, matter is being drawn inward, ever so gently. Each denser region pulls in a little of the surrounding gas and grows a little denser still, and so pulls a little harder. Across the whole dark universe, in countless places at once, gas is quietly gathering, thickening, settling toward the centers of the seeds. The dark age is when the universe assembles, in darkness, the material from which it will build its first stars. It is a strange and moving thing to picture. For a long age, there was no light anywhere in all of existence. No star had ever burned. And through that entire lightless age, gravity works steadily in the dark, drawing the cold gas together, packing it tighter and tighter in the hollows of the ancient seeds, quietly building the furnaces that had not yet been lit. The universe was preparing something in the dark, without hurry and without light, simply following the pull of matter toward matter. It is worth understanding what we are really seeing when we look at that oldest light, because it is a subtle and beautiful thing. We cannot see past the moment the fog cleared, no matter how far we look, because before that moment, the universe was opaque. So when we look out to the greatest possible distance in every direction, we arrive at a kind of wall, not a wall of matter, but the last place from which light could freely begin its journey to us. This wall surrounds us on all sides, at the edge of what can be seen, and it glows softly with the released light of the clearing. It is the boundary of sight itself. That wall is often described as a baby picture of the universe, and the description is exact. The light shows the cosmos as it was at the instant it turned clear, long before any star. And it is astonishingly smooth. Look at it in any direction, and it is nearly the same temperature, the same faint glow everywhere. This near-perfect sameness is the memory of inflation, of a time when the whole visible universe was small enough to even itself out. It is one thing to be told the early universe was uniform, and another to look at its actual portrait and see that uniformity written plainly across the entire sky. But the smoothness is not perfect, and its imperfections are the most precious part. Scattered across that faint glow are patches very slightly warmer and slightly cooler than the average, differences so small they took great care to measure. These gentle variations are the seeds, the same trembles laid down in the first instant, now made visible as tiny temperature differences in the oldest light. They are also, in a sense, frozen sound. Before the fog cleared, the tightly coupled plasma and light rang with pressure waves, and when the light was released, the pattern of those waves was frozen into it, a still photograph of the last ringing of the young universe. From those faint seeds, everything is about to grow, and it is worth holding the two pictures together. The warmer and cooler patches in the oldest light are the very same regions that, being a whisper denser, will draw matter inward over the coming ages and become the first structures. When we map the ripples in that ancient glow, and then look at the arrangement of galaxies across the sky today, we are looking at the same pattern at two different ages, the blueprint and the finished building. The galaxies remember where the seeds were. The universe grew along the lines it drew for itself at the very start. Then comes the darkness, and it is worth sitting with how complete it was. When the light departed, it did not leave behind a starry night. It left behind cold gas and nothing that shone at all, an unbroken darkness filling the whole of space. There was no point of light anywhere, no star, no glowing thing, only the fading afterglow slipping toward the cold and the neutral hydrogen drifting invisibly through the black. If one insists on picturing it, one must picture true and total dark in every direction for a very long time. The universe had made its light and then let it go, and for an age it kept none for itself. And still, in that darkness, the patient work went on. Gravity does not need to see. In the denser patches, matter drew inward, slowly, without light, gathering and thickening in the hollows of the ancient seeds. Nothing marked the progress, no glow, no warmth to speak of, only the steady inward pull, adding gas to gas across immense spans of quiet time. The Dark Age was not a pause in the story. It was the chapter in which the universe, working blind, assembled the material for its first stars, packing the cold gas ever tighter toward the moment of ignition. The longest darkness was also the deepest preparation. And as the gas gathers, in the densest of those gathering knots, the pressure and the heat at the very center begin to climb. Slowly, over long stretches of the Dark Age, one of these knots after another is squeezed tighter and warmer and tighter still, approaching, though it has not yet reached, the point at which something new becomes possible. The universe is dark and cold and quiet, but in its densest hidden centers, it is warming toward ignition. The long night is nearly over, and the first light is almost ready to return. Out of the long darkness, the first light returns, and it returns from within. Not the fading afterglow of the beginning, but new light, made for the first time by the universe itself. In the densest centers of the gathering gas, the pressure and heat have climbed high enough at last, and the first stars ignite. This is one of the great turning points of the whole story, the moment the universe begins to shine on its own. We call it the cosmic dawn, and it deserves the name. Consider what has to happen for a star to be born. In the hollows of the ancient seeds, gas has been gathering all through the Dark Age, pulled inward by gravity, packing tighter at the center. As a knot of gas grows denser, its core grows hotter, because squeezing gas heats it. There comes a point when the very center becomes hot enough and dense enough that hydrogen begins to fuse, its nuclei joining to make helium and releasing light in the process. When that fusion catches and holds, a star is born. Light pours out from the core, pushes back against the inward pull of gravity, and the star settles into a long, steady balance between the two. After the long, lightless age, the darkness is broken. The first stars, though, are unlike almost any star that shines today, and their difference shapes everything that follows. They form from the only material that exists at this point, pure hydrogen and helium, with none of the heavier elements that later stars will contain. This matters more than it might seem, because heavier elements help a gathering cloud shed its heat and break into smaller pieces. Without them, the first clouds cannot cool and fragment as easily, and so they do not split into many small stars. Instead, they collapse into a few enormous ones. The first stars are giants, far more massive than the ordinary stars of later ages. Being so massive, they live in a way that is both magnificent and brief. A great mass means a fierce, hot core, and a fierce core means the star burns through its fuel at a furious rate. These first giants shine with a brilliant blue-white light, far brighter than the sun, blazing across the newborn dark. But they pay for that brilliance with their lives. Where a modest star can shine steadily for billions of years, these giants exhaust themselves in only a few million. They are the brightest and the shortest-lived of all the generations of stars, flaring into being and then, by cosmic measure, quickly spending themselves. And when a great star like this reaches the end of its short life, it does not fade quietly. Its core collapses, and the star explodes, scattering itself across the surrounding space. In that collapse and that explosion, something happens that has never happened before in the history of the universe. The star forges elements heavier than helium and flings them outward into the gas around it. For the first time, the cosmos contains carbon and oxygen and iron and the other heavier elements made in the cores and the death throes of these first stars. This is the beginning of one of the most important threads in the entire story, and it is worth stating plainly. The universe was born with almost nothing but hydrogen and helium. Every element heavier than those, everything that will one day make rock and metal and water and living bodies, has to be manufactured inside stars and released when they die. The first stars are the first manufacturers. The carbon that will one day be woven through every living thing, the oxygen that will fill future oceans and skies, the iron that will one day sit in the core of a planet and in the blood of an animal, all of it begins here, scattered outward by the deaths of the earliest stars. There is a quiet wonder in following that thread all the way to the present. The atoms in a hand, in a leaf, in a single drop of water, were assembled inside stars. And the very first of those atoms, the earliest carbon and oxygen and iron ever to exist, were made and scattered in the universe's first few 100 million years by stars that lived and died long before the Earth, or the Sun, or even our galaxy in its present form, had come to be. We are, in the most literal way, made of the deaths of ancient stars, and the oldest of those deaths lie here at the cosmic dawn. As the first stars burn and the first galaxies begin to gather around them, their light does something to the universe at large. It reaches out across the cool hydrogen gas that fills the space between the gathering structures, and it is fierce enough to strip the electrons back off those atoms. This undoes, in a sense, the great settling that cleared the fog. The hydrogen that had become neutral atoms is now ionized once more, its electrons torn free again. But this time, not everywhere at once, and not because the whole universe is hot. It happens in growing bubbles of light around the first sources, spreading outward into the dark. This process is called reionization, and you can picture it gently. Around each of the first stars and the first small galaxies, a region of the surrounding gas is lit and stripped and made transparent, a bubble of clarity expanding into the neutral dark. As more and more stars ignite across the cosmos, these bubbles grow and reach toward one another and begin to overlap. Slowly, over a long stretch of the early universe, the bubbles merge, until most of the gas between the galaxies has been ionized, and the whole cosmos is broadly transparent once again. When reionization is complete, the universe settles into the clear, open state it will keep for the rest of its long history. The gas between galaxies is thin and ionized, and for the most part, invisible. Light can cross the cosmos freely. The Dark Age is fully over, and the fog has burned back for the last time. From here on, the universe is a place of stars and galaxies scattered through clear space, lit from within by the light of countless suns, and it will remain recognizably so for billions of years to come. There is a small piece of physics behind the birth of the first stars that is worth naming gently, because it shaped how large they grew. For gas to collapse into a star, it must be able to shed its heat, and a gathering cloud sheds heat by radiating it away. In the pure hydrogen and helium of the early universe, without heavier elements, this shedding was difficult, and gas could only cool by way of rare, faint molecular processes. Because the cooling was slow, the clouds could not easily fragment into many small pieces. They gathered into large, hot knots instead, and so the first stars came out enormous. The absence of the very elements they were about to create is what made them giants. The first galaxies grow up around these first stars, and they are not the grand spirals we know. They are small, clumpy, irregular gatherings, knots of stars and gas drawn together in the densest crossings of the dark matter web. They form early, and they merge often, combining and growing the small building blocks of the great galaxies to come. If one could see the early universe lit up, it would look ragged and busy, full of little glowing fragments finding one another, rather than the stately turning disks of the present. The order of the mature cosmos is something it grows into, slowly out of this early clumping. The growth of the central black holes belongs to this early time as well, and it remains one of the story's open questions. Somehow, remarkably soon after the first structures formed, some galaxies already held black holes of enormous mass at their centers, and how they became so large so quickly is not fully understood. Perhaps they grew from the collapse of especially large early clouds, or by feeding with unusual speed, or by merging with one another. However it happened, these central black holes were in place early, feeding on infalling gas and blazing as brilliant beacons across the young universe, lighting the era of the first galaxies with the glow of matter spiraling inward. Reionization, the burning back of the neutral fog, deserves to be pictured slowly. because it was not a single event, but a long, patchy transformation. Around each early source of light, a region of the surrounding hydrogen was stripped and made transparent, a growing bubble of clarity in the neutral dark. These bubbles expanded, and new ones opened as more stars and galaxies lit up. And over a long stretch of the early universe they spread and met and overlapped. The universe did not clear all at once, but in a slow merging of countless separate clearings, until the bubbles joined into one, and the last of the neutral gas between galaxies was lit and stripped away. While all of this unfolds, the great enrichment cycle has quietly begun, and it will run for the rest of cosmic history. The first stars made the first heavier elements and scattered them in dying. The next stars formed from that slightly enriched gas and made more, and scattered those in turn. Each generation hands richer material to the next, and the universe grows steadily more chemically capable, generation by generation, star by star. What begins here, at the cosmic dawn, as the first faint trace of carbon and oxygen will, across billions of years, become the abundant material of planets and oceans and living things. The dawn lights the first lamp of a fire that never afterward goes out. And so the character of the universe changes for good at the cosmic dawn. Before it, the cosmos was smooth, dark, and simple. After it, the cosmos is a place of separate shining things, each with its own history, scattered through clear space and slowly growing richer. The transition from the one to the other, from the featureless dark to the lit and structured universe, is the true work of this chapter. Once it is done, the universe will never again be dark and empty in the way it was. The long day of stars and galaxies has begun, and it will run, luminous and unhurried, across the ages that carry us toward home. And so the cosmic dawn closes, not with darkness returning, but with the long day of stars beginning. The first giants have lived and died, and in dying have seeded the cosmos with the first heavier elements. Their light has cleared the last of the neutral fog. The universe has learned, at last, to make its own light and its own material, and it will go on doing both, generation after generation, for ages. The gas that the first stars enriched is already drifting, already gathering again, already beginning to form the next stars, in the growing structures that will become the first true galaxies. The dawn gives way, softly, to the morning, and the morning belongs to the galaxies. Once stars exist, they do not stay alone. Gravity that gathered gas into stars now gathers stars into greater company, drawing them together with gas and with unseen matter into the first galaxies, and then drawing the galaxies themselves into ever larger arrangements. This chapter is the slow building of the architecture we still live inside, the long assembly of the structures that give the universe its shape. It is patient work, unfolding over billions of years, and it is happening everywhere at once. The building goes from the bottom up, and this is one of the important patterns of cosmic history. The universe does not make large galaxies first and break them into small ones. It makes small clumps first, and those clumps merge and grow and merge again, building larger and larger galaxies over long stretches of time. A great galaxy is not a single creation, but an accumulation, assembled piece by piece from many smaller pieces that came together across ages. The universe builds its big things by patiently combining its small things. Guiding all of this is a scaffolding that gives off no light, and that we can only know by its pull. Most of the matter in the universe is not the ordinary matter of stars and gas. It is something else, something that neither shines nor blocks light, that we call dark matter. It cannot be seen directly, but it has gravity, and that gravity shapes everything. In the early universe, this dark matter gathered first, settling into a network of dense knots and long connecting threads, and the ordinary gas flowed along that network, pooling where the dark matter was densest. The galaxies grew where the scaffolding told them to grow. The result is the largest pattern in all of existence, and it is a genuinely beautiful one to picture. The galaxies are not scattered evenly through space like grains spread on a table. They are strung along immense threads, long filaments of galaxies reaching across the cosmos, and where those threads cross, great clusters of galaxies gather. Between the threads lie enormous, nearly empty regions, vast hollows where there is almost nothing at all. This whole arrangement, the threads and the knots and the hollows between them, is called the cosmic web, and it is the framework on which the entire visible universe is hung. It is worth letting that picture settle, because it changes how one imagines the cosmos. The universe is not a random sprinkling of stars in empty black space. It is a web. Bright knots of galaxies are strung along faint, glowing threads, and those threads are wrapped around great, quiet hollows where almost nothing lives. Look at it from far enough away, and the universe resembles something grown rather than scattered. A slow structure of light and shadow, threads and voids, built by gravity over billions of years and holding its shape across all that time. At the center of most large galaxies, as they assemble, something remarkable settles into place. A black hole grows there, but not an ordinary one. These central black holes are supermassive, holding the mass of millions or even billions of ordinary stars concentrated into a single point of overwhelming gravity. How they grew so large, so early in the story, is one of the genuine open questions of this chapter, one of the places where the timeline still keeps a secret. But grow they did, and nearly every great galaxy carries one at its center. These central black holes are not always quiet. When gas falls toward one of them, it does not simply drop in. It swirls inward, faster and faster, crowding and heating as it goes, until it glows with tremendous brilliance before it finally crosses the point of no return. In the early universe, when gas was plentiful and the central black holes were feeding, some galaxies blazed with the light of this infalling material, shining as brilliant beacons that we call quasars. These were among the most luminous objects the universe has ever made, single points outshining entire galaxies, lit by matter in its final bright spiral inward. There is a curious partnership between these central black holes and the galaxies that hold them. As a galaxy grows, its central black hole grows too, and the two seem to influence one another, so that the size of a galaxy's central black hole is tied to the size of the galaxy around it. The light and the outflows from the feeding black hole can reach out into the galaxy and slow the forming of new stars, while the galaxy in turn feeds the black hole. They grow together, center and whole, in a slow and balanced relationship that spans the galaxy's entire life. As the ages pass, the galaxies take on the shapes we recognize. Many of them settle into graceful turning disks, flattened wheels of stars and gas rotating slowly, often wound through with spiral arms where new stars light up along the curves. Others, especially those built from many violent mergers, lose their disks and become smooth, rounded gatherings of older stars, ellipses without arms, their star-forming days largely behind them. The shape of a galaxy is a record of its history, of how gently or how roughly it was assembled. Mergers, it is worth saying, are ordinary events in cosmic time, and they are gentler than the word suggests. When two galaxies drift together and combine, their stars almost never strike one another. The distances between stars are so great, compared to the sizes of the stars themselves, that two galaxies can pass through each other like two slow clouds meeting, their stars gliding past in the wide gaps, rearranged by gravity, but rarely touching. A galactic merger is not a shattering, but a long, slow mingling, taking many millions of years, ending in a single larger galaxy where there were two. Across this whole age, the making of new stars rises to a great peak. There comes a time, well along in the story but still far in our past, when gas is plentiful and galaxies are building most actively, and the universe forms new stars faster than at any other time, before or since. This is the height of cosmic star formation, the brightest, most fertile stretch of the age of galaxies. It is the closest the universe comes to a springtime of making, when the light of new stars is kindled most rapidly across the whole cosmic web. And after that peak, the rate of new star formation begins a long, gentle decline. Not a collapse, not an ending, only a slow easing, as some of the gas is used up and some is heated and scattered, and the pace of making new stars slips downward, little by little, across the ages that follow. It is a decline that continues, quietly, all the way to the present day and beyond. But at this stage in the story, the decline has barely begun. The galaxies are turning, the web is bright, the central black holes have found their balance, and the universe has settled into its long, luminous middle age, still full of gas, still building, still making light. The voids between the threads of the cosmic web deserve a moment of their own, because they are as much a part of the pattern as the galaxies. These are the great hollows, regions where the early matter drained away toward the denser surroundings, leaving behind spaces that are nearly, though not perfectly, empty. They are enormous, far larger than the clusters of galaxies that ring them, and they make up most of the volume of the universe. The bright web we admire is really a thin tracery around these quiet emptinesses. If galaxies are the lit windows, the voids are the wide, dark rooms of the cosmos, and there are more of the dark than the lit. Where the threads of the web cross, the galaxies gather most thickly, into clusters, and these are among the largest bound structures in the universe. A great cluster can hold hundreds or thousands of galaxies, all moving within the shared pull of the enormous dark matter that binds them. And between those galaxies lies a thin, extremely hot gas that fills the whole cluster with a faint glow of high-energy light. These clusters sit at the densest knots of the web, gathered patiently over billions of years as galaxies streamed inward along the threads toward the crossings. They are the great cities of the cosmos, built where the roads of the web converge. The disks of spiral galaxies, turning so gracefully, are themselves a slow achievement, and it is worth appreciating how they came to spin. As gas fell inward to build a galaxy, it carried a small amount of turning motion, and as it settled and flattened, that turning grew more organized, the way a gathering swirl tightens as it draws in. Over long ages, the gas settled into a broad rotating disk, and within that disk, new stars lit up along the denser lanes, tracing the spiral arms. A spiral galaxy is not a solid pinwheel, but a slow river of stars and gas orbiting together, with the arms marking where the making of new stars is brightest. Not every galaxy keeps its disk, and the difference is written by history. Galaxies built more gently, drawing in gas quietly, tend to settle into these graceful spirals. Galaxies built through many violent mergers, on the other hand, have their disks stirred and scrambled by the combining, and they end as smooth, rounded ellipses of older stars, their gas largely spent, their making of new stars mostly finished. A galaxy's shape and color, then, are a kind of biography. The blue-tinged spirals are still forming young stars along their arms, while the yellowed ellipses hold mostly old stars, their bright youth behind them. The great peak of cosmic star formation is worth picturing at its height, for it was the most fertile stretch the universe would ever know. There came a long stretch, well back in cosmic time, when gas was abundant and galaxies were building most actively, and across the whole web, the making of new stars ran faster than at any time before or since. The universe glowed with fresh young stars, kindled in enormous numbers in galaxy after galaxy across the sky. It was, in the plainest sense, the springtime of the cosmos, the season when the most light was being newly lit. Everything after it, including our own late age, lives in the long, gentle decline that followed that peak. It is worth noticing, too, how gentle the merging of galaxies really is, against the drama the word might suggest. When two great galaxies drift together and combine, their stars pass among one another across such wide gaps that collisions between them are almost unheard of. The galaxies flow through each other like two slow clouds meeting in the dark, their stars gliding past in the emptiness, rearranged by the shared pull of gravity but rarely touching. Over many millions of years, the two settle into one, their disks stirred or scrambled, their gas mingled, a single larger galaxy emerging where there had been two. Even the largest rearrangements in the cosmos happen slowly and quietly, and without shattering the small worlds that ride within them. Threaded quietly through all of this grand activity, one ordinary galaxy is assembling in the usual way, in no special place, drawing itself together from smaller pieces and in falling streams. Its oldest stars are forming in its early building. Its disk is beginning, slowly, to settle and to spin. It will keep growing, keep gathering, keep quietly making stars across billions of years, long after the great peak has passed. And in one of its outer arms, ages from this stage of the story, the gas will gather that becomes our sun. But the universe has more elements to make first, in more generations of stars, before that quiet corner is ready. The web turns on, bright and patient, carrying its countless galaxies toward the chapters still to come. Within this great turning framework, one galaxy among the countless others is quietly assembling in the ordinary way, from smaller pieces and in falling gas, in no special corner of the web. It will one day be our own. But before we can find our way to it, the universe has more work to do, the slow work of many stellar generations, each one enriching the gas a little further, each one making the material a little more capable of building worlds. The making of the elements is the next thread to follow, and it runs quietly beneath the whole age of galaxies, star by star, across billions of years. Beneath the whole age of galaxies runs a quieter story, the slow chemistry of the cosmos. The universe was born with almost nothing but hydrogen and helium, the two lightest elements, made in its first minutes. Everything richer than that had to be built afterward, slowly, one star at a time. The carbon of every living thing, the oxygen of the air and the seas, the iron in blood and in the cores of planets, the gold that will one day lie in the ground, none of it existed at the beginning. All of it is manufactured patiently across billions of years in the lives and deaths of stars. This is the thread of how the universe grew from simple to complex. To understand it, we have to understand what a star truly is, beneath its light. A star is a place where gravity squeezes light elements together until they fuse into heavier ones, and that fusion releases the energy that makes the star shine. A star, like the sun, spends most of its long life fusing hydrogen into helium in its core, slowly, steadily, for billions of years. The outward push of that released energy holds the star up against the constant inward pull of its own gravity, and the balance between the two is what a stable star is. To shine is to hold oneself up by making heavier elements from lighter ones. But no star fuses forever. Eventually, a sun-like star exhausts the hydrogen at its center, and its balance begins to shift. The core contracts and heats, the outer layers swell enormously, and the star becomes a red giant, grown vast and cool and luminous. In this later stage, it begins to fuse helium into carbon and oxygen, building heavier elements than it made before. And then, gently, near the end, such a star sheds its swollen outer layers into space, casting off shells of gas that carry the carbon and oxygen it made, seeding the surrounding cosmos with them. What remains at the center settles into a small, dense, slowly cooling ember, glowing faintly for ages as it fades. More massive stars go much further, and their story is one of building in layers. A great star fuses hydrogen into helium, then helium into carbon and oxygen, then carbon and oxygen into still heavier elements, silicon and others. Each stage burning hotter and faster than the last. Near the end, such a star has a structure like the layers of an onion, each shell fusing a heavier element than the shell outside it, working inward toward the center. And at the very center, this building reaches a wall. The layers climb the ladder of elements until they arrive at iron, and there they stop. Iron is the end of the road, and the reason is one of the quiet turning points of physical law. Fusing elements lighter than iron releases energy, which is what powers a star. But fusing iron itself does not release energy. It absorbs it. Iron cannot be fused for profit, and so a core of iron cannot hold the star up. When a massive star builds an iron core, that core can no longer generate the outward push it needs to resist gravity. The balance that held the star up for its whole life is broken. Gravity, which has been resisted at every stage, finally has nothing left to push back against it. What follows is one of the most dramatic events in the cosmos, though we will keep it soft. The iron core collapses in on itself, and the outer layers of the star fall inward and then rebound in a colossal explosion. The star tears itself apart in a burst of light that can, for a brief while, outshine an entire galaxy of ordinary stars. We call this a supernova. And in that explosion, the star scatters everything it has made, all the carbon and oxygen and silicon and iron of its layered core, flinging it outward into the surrounding space to mingle with the gas there. The very heaviest elements of all are made in the most extreme moments the universe can produce. In the fury of these great explosions, and in the collisions of the dense remnants that stars leave behind when they die, matter is squeezed and bombarded so intensely that the heaviest elements form, the gold and the platinum and the others near the top of the ladder. These are rare events, and the elements they make are rare accordingly, which is part of why gold has always been precious. Every atom of it was forged in one of the most violent and uncommon events in all of nature, and then scattered across space to settle, eventually, into the ground of some future world. Now follow this across the generations, because that is where the pattern lives. Each generation of stars is born from gas, lives, and dies, and in dying enriches that gas with the elements it made. The next generation of stars forms from this enriched material, and so it begins its life already containing some carbon, some oxygen, some iron, inherited from the stars that came before. Those stars in turn make more, and die, and enrich the gas further. Step by step, generation by generation, the universe grows slowly more complex, its gas ever more thoroughly salted with the heavier elements, until it becomes capable of making things that the early universe never could. There is a single dying star at the base of all of this, multiplied billions of times over. One star, at the end of its life, can seed a whole region of space with the carbon and oxygen of future worlds. Do that for one star, and you have enriched a small patch. Do it for billions of stars, across billions of years, each one adding its share, and you slowly transform the cosmos, building, out of an original simplicity of hydrogen and helium, a universe salted throughout with everything needed to make planets, and oceans, and living bodies. The richness of the present universe is the sum of countless individual deaths, each one a small gift to the gas. And so, late in this long process, in a well-enriched pocket of one particular galaxy, the material is finally ready to make a star with worlds around it. Our own sun is a late arrival, a star born long after the making of the elements had been running for ages, and that lateness is exactly why it could be born the way it was. There was enough carbon, enough oxygen, enough iron and rock and metal in the gas by then to build not only a star, but a family of planets around it. An early star could not have done this. The universe had to enrich itself first, patiently, for billions of years, before it could make a place like home. Our own galaxy grew the way all the others did, gathering from smaller pieces and from streams of gas falling in along the cosmic web, its oldest stars forming in its early building, its turning disk and spiral arms settling into place across long ages. And it still carries the record of that history within it. There are streams of stars threading through it that were torn from smaller galaxies it drew in and absorbed long ago. And there is fresh gas still trickling in, keeping a slow, steady making of new stars alive, even now. A galaxy is not a finished thing, but an ongoing one, still gathering, still forming, still quietly at work. It is worth naming, gently and specifically, where the familiar elements come from, because it ties the cosmos to the body in a direct way. The carbon that forms the backbone of every living thing is made in the cores of stars built from helium in their later stages. The oxygen we breathe and that fills the seas is forged the same way in the hearts of massive stars. The nitrogen in the air, the calcium that will one day stiffen bones, the phosphorus woven through living cells, all of it is stellar work, cooked in stars and scattered when they died. The elements of life are not earthly in origin. They are stellar, delivered to a young world by the deaths of stars that came before it. The gentle ending of a sun-like star deserves a closer look because it is one of the quieter and more beautiful deaths in nature. When such a star has swelled into a red giant and fused what it can, it does not explode. It sheds its outer layers softly, casting them off into space as expanding shells of glowing gas, delicate and slow, carrying the carbon and oxygen it made outward into the surroundings. At the center, the exposed core remains, small and dense and very hot, a white ember that will simply cool over an immense span of time, fading gradually toward darkness. It is a death by exhalation rather than by blast, a slow letting go of the star's outer self. The most massive stars end far more dramatically, and their deaths are the great seeding events of the cosmos. When such a star's iron core collapses and the star explodes, it scatters its whole layered store of elements across space in a single brilliant burst, enriching an entire region at once. And in the extreme conditions of these explosions, and in the collisions of the dense remnants that stars leave behind, the heaviest elements are forged, the gold and the platinum, and the rest near the very top of the ladder. These are rare and violent moments, and the elements they make are rare accordingly. The preciousness of gold is, in the end, a fact about how uncommon the events that make it truly are. Follow this across enough stellar generations, and a quiet transformation accumulates. The first stars enriched the gas only faintly, but each generation added its share, and the gas grew steadily richer in the heavier elements, until, after billions of years and countless stellar deaths, it became capable of things the early universe could never have done. It became capable of making solid rocky worlds and metal cores and the abundant carbon and oxygen that life requires. The richness of the present universe is not a starting condition. It is an achievement built up slowly, one dying star at a time, across the whole long age of galaxies. There is a way of holding this that brings the entire timeline into a single breath. The iron in your blood was made inside a star that died before the sun existed. The calcium in your bones, the carbon in every cell, the oxygen in every breath, all of it was forged in ancient stars and scattered by their deaths, gathered up much later into the cloud that became our world. To be alive is to be made of assembled starlight, of the manufactured leavings of suns that shone and died long ago. The making of the elements is not a distant abstraction. It is the origin of the very stuff that is reading or hearing these words. There is a slow rhythm to this enrichment that is worth feeling as a rhythm rather than only understanding as a fact. Gas gathers into a star. The star shines for an age, holding its balance, making heavier elements in its core. The star dies, gently or violently, and gives those elements back to the gas. The enriched gas drifts and gathers again and makes new stars, which shine and make and die and give back once more. Around and around it goes, each turn adding a little more richness, each generation handing on more than it received. The universe breathes in this slow way across billions of years, and the breathing is what built, out of a plain beginning of hydrogen and helium, a cosmos capable of making worlds and the life upon them. And so, late in this long enrichment, in a well-salted pocket of one ordinary galaxy, the gas is finally ready to make a star with worlds around it. Our own corner is the beneficiary of everything that came before, of every earlier star that lived and died and gave its elements to the gas. An early star, born of pure hydrogen and helium, could have had no rocky planets, for the rock did not yet exist. Only after the universe had spent billions of years enriching itself could a star like the Sun be born with the material for worlds gathered around it. The making of the elements is the long preparation, and the next chapter is the small, close, familiar place it prepared. Within one unremarkable spiral arm of this galaxy, in a quiet outer neighborhood far from the crowded center, the gas is gathering that will become the Sun. It is enriched gas, carrying the gifts of countless earlier stars, the carbon and oxygen and iron of ancient deaths. It is beginning, very slowly, to draw together under its own gravity, following the same ancient pattern that made the first stars long ago in the dark. But this time, the material is richer, and what it makes will be more than a star alone. The making of the elements has prepared the way, and the next chapter belongs to the small, close, familiar corner of the cosmos that we call home. More than 9 billion years into the story, In a cloud of enriched gas and dust, drifting through an ordinary arm of an ordinary galaxy, our own corner of the universe begins to take shape. This chapter is the smallest in scale of all of them, and the closest to home, and it is worth remembering, as we arrive, how late it comes. The sun and the earth are not part of the universe's beginning. They are latecomers, formed after the cosmos had already been making stars and elements and galaxies for billions of years. Everything here is built from what the earlier chapters left behind. It begins, as the first stars began, with a cloud collapsing under its own gravity. But this cloud is different from the pure hydrogen and helium of the cosmic dawn. It has been enriched by generations of stars that lived and died before it, salted with carbon and oxygen and iron and dust. As this cloud draws inward, its center grows denser and hotter, exactly as in the ancient pattern, until the core becomes hot enough for hydrogen to fuse and a new star ignites. The sun switches on, settling into the same long balance between the push of its light and the pull of its gravity that stars have kept since the beginning. Around the newborn star, the leftover material does not simply fall in. It spins, and as it spins, it flattens, settling into a broad turning disk of gas and dust circling the young sun. This disk is the birthplace of everything else in our corner of space. Within it, the tiny grains of dust, made of the heavier elements from ancient stars, begin to drift and touch and stick. Grains gather into clumps, clumps into pebbles, pebbles into boulders, and boulders, over long stretches of time, into worlds. The planets are built from the dust of the disk, assembled quietly around the turning sun. Where each kind of world can form depends on warmth, and this gives our corner its arrangement. Close to the young sun, it is too hot for ice to survive, and only rock and metal can hold together. So the worlds that form there are small and stony. Farther out, beyond a certain distance, it is cold enough for ice to endure. And there the worlds can grow much larger, gathering not only rock and ice, but thick envelopes of gas, becoming giant planets with deep atmospheres and many moons. The pattern of our neighborhood, small rocky worlds near the warmth and great giants in the cold, is written by the simple fact of how far the heat of the sun reaches. One of the small rocky worlds settles at a gentle distance from the sun, neither too near nor too far. It is close enough to be warmed, far enough not to be scorched, in the narrow band where water can remain liquid rather than boiling away or freezing solid. Over long ages, this world gathers oceans and an atmosphere, and its surface becomes a place where liquid water can rest and flow. It is an ordinary world by the measure of the cosmos, one among an enormous number. But its particular distance from its star gives it a quiet and rare gift: the possibility of a temperate surface. Everything that makes this world, and everything that will ever live upon it, was forged in the earlier chapters of the story. Consider it plainly, for it is the thread that ties the whole timeline together. The iron in the world's core was made inside stars that died before the sun was born. The carbon and oxygen in its air and its seas were made the same way, scattered by ancient stellar deaths and gathered into the disk that built the world. The water itself is assembled from hydrogen made in the universe's first minutes and oxygen made in the cores of long-dead stars. This world, so far from the cosmic dawn in time, is built entirely from the gifts of what came before it. And on this one world, as far as the timeline can yet say for certain, matter does something it may have done nowhere else nearby. It arranges itself, slowly, over long ages, into living things. Simple at first, and then less simple, life takes hold on the temperate surface and spreads through the oceans, and across the land. This is the part of the story where our certainty grows thin, where the universe keeps its counsel, because we do not yet know how common this step is, or how rare. We know only that here, on this one small world, the arranging of matter into life did happen, at least this once. And much later still, so late that it is barely a moment ago by cosmic measure, that life arranges itself into beings who can look up. Creatures appear on the temperate world who can turn their attention to the sky and wonder at it, and slowly learn to read it. They come to measure the faint oldest light falling from all directions. They come to understand the making of the elements in the stars, and the gathering of galaxies, and the long expansion of space. From their small, late vantage on one ordinary world, they reconstruct the whole story backward, all the way to its first instant. There is a quiet symmetry in that, worth holding gently. The universe spent more than 9 billion years making the ingredients before the Earth could exist, and then a while longer still before anything on the Earth could look back and understand. We arrive very late to a story already immensely deep in progress. We are not its authors and not its beginning. We are made of its earlier chapters, assembled from the leavings of ancient stars, set down on a small, warmed world in a quiet arm of one galaxy among a great many. And yet, being late is not the same as being unimportant to the telling. The universe made, in us, and perhaps in others we have not met, a way of noticing itself. The same atoms that were forged in the first stars and scattered by their deaths have been gathered, here, into eyes that can watch the sky and minds that can follow the timeline. The long chain of cosmic history, running from the first instant through the making of the elements to this small world, has produced, at its late and quiet end, something that can trace the chain itself. That is a strange and gentle thing for a universe of hydrogen and gravity to have done. The turning disk around the young sun did more than build planets, and it is worth following what became of its leftovers. Not all of the disk was gathered into worlds. A great deal of smaller debris remained, rocky fragments and icy bodies that never joined a planet, and much of it survives to this day, circling the sun in belts and distant reservoirs. The rocky fragments drift mostly between the small worlds and the giants, while the icy bodies gather far out in the cold, occasionally falling inward to pass close to the sun as comets. These leftovers are the unused material of our own construction, the crumbs of the disk, still orbiting after all this time. Those leftovers may have played a gentle part in making our world hospitable, and it is a quietly appealing idea. The young rocky Earth formed close to the warmth, where much of the water would have been driven off, and yet it came to hold oceans. Some of that water, and some of the other light materials of life, may have been delivered later, carried inward by icy bodies from the colder outer regions that struck the young world and gave it their volatiles. Whether much or little arrived this way, the picture is a pleasing one of a world gathering the ingredients of its seas partly from the far cold edges of its own solar family. The particular distance of the temperate world from its star is worth dwelling on because so much depends on it. Too close, and the water would boil away, leaving a hot, dry world. Too far, and the water would freeze hard, leaving a cold, still one. Our world settled in the narrow band, where water can remain liquid, neither boiling nor freezing, and it is this liquid water, more than almost anything, that made the surface a place where life could take hold. A modest shift inward or outward would have given a very different world. The gentleness of our own is, in part, a matter of a fortunate distance from a steady star. The lateness of life is one of the quiet themes worth holding here. The universe existed for more than 9 billion years before the Earth formed, and the Earth existed for a long stretch before life upon it grew complex, and complex life existed for a very long time before anything appeared that could look up and wonder. Each of these steps took its own great span of time. We are not merely late to the universe. We are late even to our own world, a recent development upon an old planet circling a middle-aged star in a mature galaxy in an aging cosmos. The whole long chain had to run nearly its full length before we could arrive to notice it. And there is something worth saying about how thin our certainty grows at exactly this point, without letting it trouble the rest. We know a great deal about the first instant, the first minutes, the making of the elements, the gathering of galaxies. These we can read across the whole sky. But the step from ordinary matter to living matter, and from living matter to matter that can wonder, we have witnessed only once, here, on this single world. We do not yet know how common it is, or how rare. It is the one part of the timeline where the universe has shown us a single example and kept the rest of its answer to itself. For now, though, the story rests at our own doorstep, and it is a gentle place to pause. The sun shines steadily, holding its long balance as it has for ages and will for ages more. The small, warmed world turns beneath it, carrying its oceans and its living things through a quiet arm of the galaxy. The wider universe turns on around them, still bright, still full of stars, having brought its immense history at last to the ordinary corner where we happen to live. And it is from this small vantage, made of ancient starlight, that the whole story can be seen and traced, backward to the first instant, and forward into the deep reaches of time. For now, though, the story stands at our own doorstep. The sun shines steadily, holding its long balance, as it has for a good while and will for a good while more. The small, warmed world turns beneath it, carrying its oceans and its living things through the quiet arm of the galaxy. And the wider universe turns on around them both, still full of stars, still bright, still making light, having brought its long history at last to the ordinary corner where we happen to live. The next chapter is the one we stand inside, the present age of the cosmos, and it is a gentler and more spacious place than either its beginning or its distant end. This is the chapter we live inside. After the fury of its beginning, after the cosmic dawn and the great age of building, the universe has settled into a long, bright, gently declining maturity. It is neither young nor old. By the measure of cosmic time, it is closer to the middle of the day than to the evening. The most active building is behind it, but the sky is still full of stars, still full of light, still slowly making new suns. If there is a best chapter for looking up, it may well be this one. Nearly 14 billion years have passed since the first instant. The universe is filled with galaxies, most of them past their peak of star formation, but still shining, still turning, still forming new stars at a slower and gentler rate than in their youth. Our own galaxy is one of these, a turning disk of a few 100 billion stars, with the sun and its worlds carried slowly around its center. And our galaxy is one among a number of galaxies so large that no one can truly hold it in mind, scattered across the cosmic web out to the limits of what we can see. Those limits are worth pausing on because they are stranger than they first seem. We can only see the part of the universe whose light has had time to reach us since the beginning. This region is called the observable universe, and one might expect it to stretch about 14 billion light-years in every direction, one for each year of cosmic history. But it reaches much farther than that, because space itself has been expanding while the light traveled. The galaxies whose ancient light arrives now have been carried by that expansion to distances far greater than the light alone could suggest. The observable universe is wider than its age in years, a subtle gift of the stretching of space. We live in what is often called the Age of Stars, the stelliferous era, the long stretch of cosmic time in which stars are being born and shining and dying across the universe. Nearly everything in the whole story that involves light and warmth and the possibility of life takes place within this era. It is a long chapter, far longer than everything that came before it, and we sit somewhere within its bright expanse. But long as it is not endless. The Age of Stars had a beginning at the cosmic dawn, and it will, in the far future, have an end. For now, though, it is simply the world, luminous and turning and full. There is one feature of the present universe that reaches quietly into its future, and it is among the most surprising things ever discovered about the cosmos. Space is not only expanding, its expansion is speeding up. The distant galaxies are not merely drifting apart, they are drifting apart faster and faster as time goes on, as though something were gently pressing space to grow. For most of cosmic history, the pull of matter worked to slow the expansion, but at some point the acceleration took over, and now it governs the largest motions of the universe. Whatever is driving this acceleration behaves like an energy woven into empty space itself, present everywhere, pushing gently outward. We call it dark energy, though the name is really just a marker for how little we understand it. It is the largest single part of the universe's contents today, outweighing all the matter, both ordinary and dark, combined. And yet, what it truly is remains unknown. It is the great open question of the present chapter, the mystery sitting quietly at the center of the age we live in, shaping the future of everything while keeping its own nature hidden. The consequence of this acceleration is profound, though it unfolds with immense slowness. Over enormous spans of time, the speeding expansion will carry the distant galaxies ever farther away, faster and faster, until eventually they drift beyond the reach of our sight entirely. The sky, over ages far longer than the present age of the universe, will slowly empty of distant light, until only our own local family of galaxies remains visible, and everything beyond has receded past seeing. That emptying lies unthinkably far ahead, but its beginning is already written into the acceleration we measure now. It is worth holding, against that far future, how fortunate the present chapter is. We live in the bright middle of the story. It is late enough that the elements exist, that worlds can form, that a warmed planet can carry oceans and living things. And it is early enough that the sky is still full of distant galaxies, their ancient light still arriving, the cosmic web still visible in every direction. A being who looked up in the far future would see a nearly empty sky. We look up and see the whole crowded, luminous universe. In a real sense, this is the best chapter for looking, and we happen to be here for it. Closer to home, the present universe holds a gentle future for our own galaxy. Our galaxy and its nearest large neighbor are drifting slowly toward each other, and in the far future, the two will meet and combine into a single greater galaxy. It will be a slow and graceful merging over an immense stretch of time, not a collision of worlds, for as we have seen, the stars in merging galaxies almost never strike one another. They will simply be rearranged, gliding past in the wide gaps, until where there were two turning disks, there is one larger gathering of stars, settling into a new shape. The sun, too, carries a future written quietly into it, and it is a long one. For now, our star holds its steady middle age, fusing hydrogen calmly at its core, warming the small world that turns around it. In the far future, when its central hydrogen runs low, it will swell into a red giant, growing large and cool. And then, gently, it will shed its outer layers into space and settle into a small, dense, slowly cooling ember, glowing faintly for ages as it fades. That ending lies billions of years ahead, far beyond any present concern, a soft and distant close to our own star's long life. The sheer size of the observable universe is worth trying to hold gently, because it puts the present chapter in scale. Within the region whose light can reach us lie a number of galaxies so large that it defeats any ordinary comparison. And each of those galaxies holds many billions of stars, and a great many of those stars hold worlds of their own. Our own galaxy, with its few 100 billion stars, is a single, ordinary member of this immense gathering. When we look up on a clear night, the handful of stars visible to the unaided eye are all near neighbors within our own galaxy, the faintest sampling of the whole. The true extent of it lies far beyond what any eye can take in. Our galaxy is not alone, but belongs to a small family, and this nearness matters for the future. A modest group of galaxies moves together, bound by their shared gravity, with our own galaxy and one large neighbor as its major members, surrounded by a scattering of smaller companions. This local family is held together tightly enough that the accelerating expansion of the wider universe will not pull it apart. As the distant galaxies drift away over the ages, this near family will remain, drawn together rather than apart, eventually merging into a single greater galaxy. What is close and bound stays together, even as what is far recedes. The stretching of space reaches into every distant light we receive, and understanding it deepens the view. The light from a far galaxy has traveled through expanding space for a long time, and that expansion has drawn out its waves and reddened its color along the way. The farther the galaxy, the more its light has been stretched, and the further back in cosmic time we are seeing it. To look far into space is therefore to look far into the past. The most distant light we can gather left its source when the universe was young, and it arrives now, reddened and faint, a message from an earlier chapter, delivered across billions of years. There is a real fortune in the particular chapter we occupy, and it is worth appreciating rather than taking for granted. We live late enough that the elements exist and worlds can form, and a warmed planet can carry life. And we live early enough that the sky is still full of distant galaxies, their ancient light still arriving, the cosmic web still traceable in every direction. A being who looked up in the far future, after the accelerating expansion had carried the distant galaxies out of sight, would see only a nearly empty sky and might never guess at the wider universe at all. We look up and see the whole crowded, luminous cosmos. This is a rare and favorable window for looking, and we happen to stand within it. Even the oldest light of all is still with us in the present, which is a quietly astonishing thing to hold. The afterglow of the clearing of the fog, released when the universe first turned transparent, is still arriving from every direction this very night, cooled by the long expansion into a faint whisper of microwaves. It falls on everything, unnoticed and constant, the persistent hum of the universe's infancy reaching into its mature present. The beginning has not vanished into the past. Its light is still on its way, still touching the present chapter, still bathing the whole sky in the faintest possible glow of what once was fire. So the present chapter is a spacious, lensal one, held between a fierce beginning and a distant, quiet end. The universe is bright and turning. The galaxies are full of stars. The oldest light still falls from every direction, and the newest light is still being kindled in forming suns. The great questions, like the true nature of dark energy, sit open and unhurried, waiting. There is nothing in this chapter that presses or alarms. It is the long, luminous middle of a very long story, and we are living in it, made of its earlier pages, watching it turn. And beyond it, far beyond, lies the last chapter of all, the one the universe has not yet written, where the story runs on into the deepest reaches of time. The story does not end at the present. It runs on, into stretches of time so long that the whole bright age we live in, stars and galaxies and all, is only its brief opening scene. This final chapter follows the timeline forward, past everything familiar, into the deep future, where the universe grows slowly, darker and quieter and colder. But it is not an ending of violence. It is a long and gentle. The first thing to fade is the making of new stars, and its fading has already begun. We have seen that star formation passed its peak long ago and has been in slow decline ever since. That decline simply continues. As the ages pass, the gas that makes new stars is gradually used up, or heated, or scattered too thin to gather, and fewer new stars are born. The rate slows and slows across immense stretches of time, until at last the universe forms its final new star, and after it, no more follow. The long fertility of the age of stars quietly comes to its close. After that, the existing stars simply live out their lives and are not replaced, and one by one they go out. The great bright stars burn fastest and leave first, as they always have. The ordinary stars follow in their turn. And the smallest, coolest, most frugal stars, which sip their fuel so slowly, last the longest of all, glowing dimly for spans of time almost beyond imagining, long after their brighter kin have gone dark. But even they, in the end, exhaust themselves. The last of the small stars fades, and with it the age of starlight closes. With the stars gone, the universe enters a long twilight, lit only by the cooling remnants of what once shone. There is something quiet and almost tender in this, if one lets the fear fall away. There will come a time, far beyond any imagining, when the last star fades from the sky and the universe holds no new light at all. And still, it will go on. It will be dimmer and colder and emptier, but it will not be nothing. The remnants will remain, cooling in the dark, and time will keep flowing, as unhurried as it has always been. What remains in this twilight are the dense leftovers that stars leave behind. There are the slowly cooling embers of sun-like stars, and the dead cores of others, and the black holes left by the greatest stars and gathered at the centers of galaxies. This long stretch is sometimes called the Age of Remnants, and it is a spare, still time. The fireworks are over. What is left endures quietly, radiating away its last warmth into a darkness that grows ever deeper around it. Even the galaxies themselves come apart, over spans of time long enough to allow it. The gravity that gathered them is not quite perfect at holding them forever. Across immense ages, the remnants within a galaxy slowly rearrange, some flung outward into the growing emptiness, others drawn inward and swallowed by the great black hole at the center. The tidy structure loosens. The galaxies that once turned so beautifully thin out and disperse, until the grand architecture of the cosmic web, built with such patience in the age of galaxies, has quietly relaxed away. And even the black holes, the most enduring things of all, do not last forever. This is one of the strangest and gentlest ideas in the whole far future. Black holes are thought to very slowly leak away their energy, giving it up in the faintest possible trickle over spans of time so long they defeat comparison. Across those unthinkable ages, a black hole shrinks, ever so gradually, and finally, after an almost endless wait, it evaporates entirely and is gone. Even the deepest wells of gravity, in the fullness of enough time, quietly disperse into the dark. What the mainstream picture expects, at the far end of all of this, is a universe grown cold and thin and still. Matter is spread so widely that almost nothing ever meets anything else. Temperatures ease toward the lowest possible. The universe settles into a uniform, quiet, calm, everywhere nearly the same, everywhere nearly at rest. This gentle final state is often called the heat death, though the name sounds harsher than the thing itself. It is not a fire and not a crushing. It is a spreading out, an evening out, warmth flowing from where it gathers until it is shared so evenly that nothing further can happen. It helps to picture it not as a catastrophe, but as a settling. All through its history, the universe has been letting warmth spread from where it is concentrated toward where it is not, from hot stars into cold space, easing always toward balance. The far future is simply the end of that long easing, the point where the spreading is complete and everything rests at the same faint temperature. It is the quietest possible state, reached not by destruction, but by the patient working out of the same gentle tendency that has been present from the beginning. And yet the far future is the one chapter still genuinely unwritten, and honesty asks that we hold it open. Other endings are imagined, and none can be ruled out. In some, the accelerating expansion grows so strong that it eventually pulls everything apart. In others, the story is not a single line, but a circle, and an ending gives way, somehow, to a new beginning, another first instant, another slow unfolding. We do not know which of these, if any, is true. The universe keeps the ending of its own story to itself, and we are left to wonder gently at the possibilities. But whatever the true ending, it lies unthinkably far ahead, and that distance is itself a kind of comfort. Between this night and that final quiet stretches an ocean of time so wide that the mind cannot cross it. In all of that time, the universe is still bright, still turning, still making warmth, still carrying its stars and its worlds through the long middle of its life. There is no hurry anywhere in it. The ending, if it is an ending, is so far away that it need weigh on nothing and no one. There is only the long, slow, luminous present going quietly on. To follow the far future honestly, one has to let go of ordinary timescales entirely, and there is a strange peace in doing so. The whole bright history we have traced, from the first instant through the making of the elements to the present, spans not quite 14 billion years. But the chapters still to come are longer, far longer, by amounts that dwarf everything before them. The age of the small, frugal stars alone will outlast the present age of the universe many times over. And the ages beyond that, the long twilight of remnants and the slow fading of the black holes, run to numbers so large that 14 billion years, the whole of cosmic history so far, becomes a rounding error within them. We stand very near the beginning of time, not the middle. The naming of the far eras helps the mind hold their sweep, and each is gentler than it sounds. First comes the long age of stars we live in, the era of shining suns, which will last as long as new stars keep forming and old ones keep burning. When the last star has faded, the universe enters the age of remnants, lit only by cooling embers and dead cores and the faint glow of matter falling toward black holes. And after that, across spans almost beyond naming, comes the age of the black holes themselves, when they are nearly all that remains, slowly leaking their energy away. Each era is quieter and cooler than the one before, and each is far longer, the universe settling by stages into an ever deeper calm. The very slowness of the black holes fading is worth sitting with, because it is perhaps the gentlest idea in all of physics. A black hole does not vanish in an instant. It gives up its energy in the faintest imaginable trickle, so slowly that for most of its existence it seems utterly permanent. Only across spans of time so vast they cannot be pictured. Does it shrink? Gradually, patiently, until at last, after an almost endless wait, it is gone. Nothing in the universe is more enduring than a black hole, and yet even a black hole, given enough time, quietly disperses. Permanence, in the end, is only a matter of how long one is willing to wait. There is a way of understanding the whole direction of this that turns it from something bleak into something almost restful. All through its history, the universe has been letting warmth spread from where it is concentrated toward where it is not. Hot stars pour their heat into cold space. Energy gathered in one place eases outward toward balance. Every event in cosmic history, in a sense, is a small step in this long spreading out, this evening of warmth across the whole. The far future is simply the completion of that easing, the point at which the spreading is finished and everything rests at the same faint temperature. It is not a wound inflicted on the universe. It is the universe, finally, at rest. And because this final rest lies so unthinkably far ahead, it asks nothing of us and weighs on nothing. Between this night and that last quiet stretches an ocean of time so wide that every star now shining will live and die within it many times over, and still there will be time beyond counting. In all of that time, the universe is bright and turning and warm, carrying its stars and its worlds through the long middle of its life. There is no hurry in any of it, and no alarm. The ending, if it is an ending at all, is so distant that it belongs to no one, and it need trouble no night, least of all this one. It is also worth remembering, softly, that the far future is the one chapter still genuinely unwritten. The long, cold rest is what the mainstream picture expects, but the universe has not yet shown us its final page, and other endings remain possible. In some, the accelerating expansion eventually grows strong enough to draw all things apart. In others, the story is not a line but a circle, and a new beginning follows the ending. Another first instant, another slow unfolding of stars and galaxies and worlds. We do not know which, if any, is true. The universe keeps the close of its own story to itself, and leaves us to wonder gently at what might lie past the edge of what we can see. Whatever that ending, we are held, for now, in the long, luminous middle, and that is a fortunate place to be. We are late enough that the elements exist, and worlds can form and life can look up. We are early enough that the sky is still crowded with distant light, and the whole cosmos lies open to view. The far future is real, and the far past is real, and between them turns the bright and unhurried present, made of everything that came before and pointed toward everything still to come. There is nowhere in all of that long story that this night needs to hurry toward, and nothing in it that this night needs to carry. And so we have followed the whole of it, from the first hot instant to the last dim light, 13.8 billion years of history, and the far longer reaches beyond. The universe goes on turning, far from any ending, still bright, still making warmth in the long middle of its story, the same story that made the atoms behind your eyes. There is nothing here you need to carry, and nowhere this night needs to go. Let your breathing slow. Let the long quiet settle over you, the same quiet that fills the space between the stars. Rest now, held gently in the middle of a very long story. Sleep well, and good night.